Welcome to Unit 7, or Unit 7, Lesson 7, Practice with Rational Bases. When we talk about rational bases, it means we're going to be working with fractions and integers. Possibly in the homework, you'll see a little bit with decimals, but no problem. Most decimals are rational. It's the ones that never end and never repeat that are not rational. When we look at this one, the first one, which one doesn't belong? Well, you could take your pick on these ones. The first one, this is the only expression that's using a quotient of powers, but it has the same bases. This one's also quotient of power, but the bases are not the same. So we could use the shortcut of subtracting exponents here, but not here. This one right up here, the 3/4 to the -5th times 3/4 to the 8th. This is the only product of powers, the only one with that visually there. And then this one is the only power of a power. So that's what we're really looking for there. In the exponent rule practice, you're told that you can choose 6 of the following to write using single exponent notation. What we're really looking for in this first column is we're practicing product of powers, and then we're practicing quotient of powers, if I could spell it. And then power of a power. And so we get to practice those pieces where we see that the bases are the same, and so we can just simply add the exponents in product of powers. So this would be 7 to the 5th plus the 6th, making this 7 to the 11th power. 3 to the -3rd plus the 8th would be 3 to the 5th power. And you see with those examples, we continue on. 2 to the -4th plus the -3rd would be 2 to the -7th. And then don't miss this on the fractions. This says 5 to the 6th power. So we have to recognize that this is still in parentheses, 5 to the 6th power being raised to the 4th plus 5th power, which would give us, imagine if we wrote it like this, with just the 9th power here on top, and what that would read out as 5 to the 9th power divided by 6 to the 1st power. With the parentheses, it groups it together and makes it all to the 9th power. I'm just going to select a couple of these ones here, but hopefully you get the idea with quotient of powers. We see the same bases, and so we can take the exponents and subtract. So 5 minus 28 gives us 3 to the -23rd power. Actually, I'll do all of these ones for you. 2 to the -5th minus the 4th gives us 2 to the -9th. Be careful on these ones. This is where I see a lot of mistakes happening. 6 to the 5th minus -8. Again, mistakes. We want to make sure we have 5 subtracting 8, or subtracting -8, not just 5 subtract 8. This gives us 6 to the 13th power. 10 to the -12th minus the -20th. Remember, you can always add the opposite to give us 10 to the +8th with that one. Under power of a power, we recognize that we can go ahead and take the 2 exponents and just simply multiply them together. 7 to the 2nd raised to the 3rd would be a value of 7 to the 6th. 4 to the 3rd raised to the -3rd would give us a value of 4 to the -9th. 2 to the -8th raised to the -4th would give us 2 to the 32nd. And then 6 to the -3rd raised to the 5th would give us 6 to the -15th. A whole bunch of practice using addition, subtraction, multiplication, but also practicing with these values of product of powers, quotient of powers, and power of a power. We can skip the second problem because we didn't skip anything in that problem. Looking at the next one, we can choose 3 of the following to write using a single positive exponent. There's 2 ways that we can really do this, but positive exponent is what we want to focus on. As we look at this 2 to the -7th power, we need to be thinking about the reciprocal of this value. So the first thing that I can be thinking of is the reciprocal of 2 is 1/2. And then that 1/2 will be multiplied by 1 7 times. Likewise, we can simplify this. 1 to the 7th power is just simply 1 divided by 2 to the 7th power, which we're not going to calculate because it's really a large number and we don't need to worry about that. So watch for the pattern here. Again, negative power, negative exponent. We're going to be thinking reciprocal of 3 is 1/3 raised to now the positive power, positive 23. I could write that also as 1 divided by 3 to the 23rd power, because 1 to the 23rd power is 1. So this one is a single exponent form, single positive exponent form. This one likewise is a single positive exponent form. We'll just follow the same process that we looked at here with taking these and writing them by their reciprocal first, raising it to the positive power, and then simplifying it to represent what was being done. Again here, reciprocal is 1/4 raised to the 9th power is equal to 1 divided by 4 to the 9th power. 2 to the negative 32nd would be 1/2 raised to the 32nd power, or 1 divided by 2 to the 32nd power. And then finally, 8 would be changed to 1/8 raised to the 3rd power, which would then become 1 divided by 8 to the 3rd power. Okay. Looking at number 4, we can choose, this says choose 3 to evaluate. I'm not going to just do 3 again, but when we're talking about evaluate, that means we want to simplify so that there's no more exponents. When we look at 10 to the 5th divided by 10 to the 5th, this is a numerator being divided by the exact same denominator. We know that anything divided by itself is always equal to 1. For letter B, we're taking 2/3 raised to the 3rd power. I could write this out as 2/3 times 2/3 times 2/3, or I could simply say 2 to the 3rd power divided by 3 to the 3rd power would be equal to 8 divided by 27. And that would be our simple form of that, or our evaluated form. Looking at letter C, I see product of powers, same bases being multiplied together. I can simply add the exponents. And I know that 8 plus negative 8 is 0. And I know anything to the 0 power will be equal to 1. When we come to the evaluate part of this, we would not want to stop here at 2 to the 0 power. We want to take it all the way to 1. Looking at this one right here in letter D, this one would be 5 to the 2nd power divided by 4 to the 2nd power, which gives us 5 times 5 is 25, 4 times 4 is 16, and we're done with that one. Letter E, we see 3 to the 4th power as the new base being raised to the power of 0. Again, go back to this power of 0 thing. That's a pretty cool step right here. We could be thinking 3 to the 4th times 0, or we could just be thinking 3 to the 0 power, which is equal to, you guessed it, 1. Looking at letter F, let's think mentally what we could do with this. This is 7 to the 2nd power is 49, 7 times 7. 2 to the 2nd power is 2 times 2 is 4. The work for this would look like this, 7 to the 2nd power divided by 2 to the 2nd power. Cool. Looking at the last step of it, true or false, we're going to talk about inconsistent bases. Mark each equation as true or false. What could you change about the false equations to make them true? Looking at this one right here, 1/3 raised to the 2nd power times 1/3 raised to the 4th power looks like product of powers. I see the same bases being multiplied, so the exponents can simply be added. 2 plus 4 is 6. This is a true statement. Looking at this next expression, or this next equation, 3 to the 2nd power times 5 to the 3rd power is equal to 15 to the 5th power. That one has me a little worried because I don't see product of powers to be useful here. So what I want to do is just verify and see if this is a true statement or not. 3 to the 2nd power becomes 9 times 5 to the 3rd power is 125. 15 to the 5th power is a really big number. In fact, let's see here. I'm not going to go 15 times 15 times 15 or anything like that. I want to be able to use my calculator correctly. 15 raised to the, I click that button that says x to the y, raised to the 5th power is equal to 759,375. That's a really, really big number. So what could I do to actually do this? Well, 9 times 125 is 1,125. I'm a little curious if that one can be taken as a square root or a cubic root possibly. If I take the square root, it doesn't come out very nicely. But if I go, let's see if this one has a cubic root. It does not. What I would have to do is kind of play with this and decide what to do with them. I could just say 3 to the second power divided by, or times 5 to the third power is equal to 1,125. And that would be a true statement. So possibly, there's a lot of things that I could possibly think about with this to make some changes to make it true. But the bottom line on this one is there's really nothing that I can do differently. I mean, I could work my way through it and try and find another power that would work with this, but I don't think that I would necessarily be able to find a good power right away to work with this. So just make it a true statement simply by that. Looking at this next one, number 3, 5 to the 4th power plus 5 to the 5th power is equal to 5 to the 9th power. That one again, they're trying to trick us. First thing I see is if this was a product of powers, this would be super easy to go with. But since it's not, this is going to be a false statement. I know that because let's bring this calculator back up. 5 to the 4th power, let's do this. 5 to the 4th power plus 5 to the 5th power is equal to 3,750. And 5 to the 9th power, is equal to over 1 million. So clearly this is not a true statement. But if I just simply changed it, 5 to the 4th times 5 to the 5th is equal to 5 to the 9th. Now it's a true statement. The next one that I'm after, I want to be able to think about these pieces in a little bit different light again. I want to verify. Right now, my gut tells me this is a false statement. I want to verify this. Go 1/2 raised to the 4th power would be 1/16 times 1,000. So 1/16 of 1,000 would be 1,000 divided by 16. So 62.5. That tells me 62.5 should be equal to whatever 5 to the 7th power is. I'm thinking probably not equal. Yeah, 7,800 or 78,125. Not a true statement. So definitely we know this is false. And because that's false, I need to go ahead and do a little bit of work to make this work. So I have some options that I can do. I can again check for a square root. That's not going to work. I can check for a cube root. That's not going to work. I could play with it and try and find something that will work, or I can simply just go with what I had before and say that 1/2 raised to the 4th power times 10 to the 3rd power would be equal to 78,125. The last one, again, doesn't look like it's quite right from the beginning. It looks like all they did is multiply the bases and then just kept the exponent. Let's see what happens. 3 to the 2nd power can simplify or evaluate that to 9 times 5 to the 2nd power is 25. And 15 to the 2nd power is 225. And I believe that's actually a true statement. 9 times 25 is 225. So this is a true statement. So the big story is this: don't judge a book by its cover. Just because it doesn't look true based on the rules we've been using doesn't necessarily mean that it's false. So be careful with that. This last one, are you ready for the lesson? I'm going to just get you started with it, but I want you to finish it on your own. What we know about this is if we're going to solve the equation, we need these two expressions to be equal to each other. To do that, we have to figure out the right value of x. What we know is that 3 raised to the x minus 5 can be equal to 9, which we can break that down to 3 to the 2nd power. So we're going to replace or substitute 9 with 3 to the 2nd power, but it's still raised to that x plus 4 power. With the rule of power of a power, I can simplify this to say 3 to the x minus 5, the left expression is fine, is equal to 3 raised to the power of 2 times the sum of x and 4. Okay, multiplying the powers together. And then I have the same base. Now all I have to do is get my exponents to be equal. And you can do that by solving for x. So you finish that up, find out what does x equal, and then it should come out true. All right, so the past few lessons, we found a lot of rules to help us easily keep track of repeated factors when using exponents. We've extended these rules to make some sense with negatives. We've worked a lot with the fact negative exponents and the factor or the fact of the reciprocal of the base. And then we have this pieces about defining a number to the power of 0 is always equal to 1. We have exponent rules. These are the exponent rules that we can follow. The first one, product of powers. And the reason we call it product of powers is because we're taking two powers multiplied together, therefore we get a product of powers. The next one, we take a power raised or multiplied, we take an exponent, power as a base, raised to another power, so we call this one a power of a power, a single power. This next one, we have division of two powers, so we call this a quotient of powers. We have a negative exponent. And we need to be thinking about this in terms of reciprocal. And then finally, we have what we call the 0th power equals 1. X can be any positive number in the world, no matter what it is. In this lesson, we practiced using these exponent rules for a different base and exponents. And so as we go through this, as we be thinking about this, that's really all the further we need to think. There's a couple other rules that are going to be there on your test, but that's it for this lesson. Thanks for tuning in. Let me know if you have any questions and how I can help. Take care.